Summation notation. In each of the previous examples, we were repeatedly adding terms. To simplify this computation expression, we introduce the summation notation. Let's go to the formal definition. A typical way to list a sum of many terms is called the sigma or summation notation. For the finite case, we write this Greek symbol called sigma, and we say k equals 1, so that's the starting point. Those are also called the indices of summation, and at the top of it we write n. That's where we stop. The numbers for the indices are integers like 1, 2, 3, 4. So the summation notation gives us a nice compressed way to express the list of the terms we're adding together. Example, let's try this. Find the value of the summation of n equals 1 to 3 of the expression 5n minus 2. Our solution. Let's begin by writing that notation again just so that we get comfortable with it. The summation of n equals 1 to 3 of 5n minus 2. We begin at n equals 1 and put the 1 in the place of n. So the first term would be 5 times where the n was, we put in 1 minus 2. Now we go to the next integer after 1 would be 2. And so we take that expression and we would write 5 times where the n was, we put in 2 minus 2, and do it again for the last one. We stop at 3, that's the number on top. So we'll have 5 times 3 minus 2. Let's do each of the computations in the brackets. So 5 times 1 is 5, 5 minus 2 is 3. The next one is 8, 5 times 2 is 10. 10 minus 2 is 8, and the last one is 5 times 3 is 15, and 15 minus 2 is 13. Add those three numbers together. 3 plus 8 plus 13 is 24. Example. For the function f of x equals x squared plus 1, and given the extended sums for L sub 4 and R sub 4, remember this is adding up rectangles, L for the left end corner, R for the right end corner, we're going to express both of these using summation notation. So let's look at what we've had. L sub 4 was equal to, the 0.5 was the width or the delta x of each of the rectangles, and we multiplied it by the height where the height of the rectangle on the left-hand side touched the graph of the function. So the solution here is we need to generate the grid point values of the 0, the 0.5, the 1, and the 1.5 that we evaluate in the function. Let's look at a number line. We've got a number line with 0, 0.5, 1, 1.5, 2, 2.5. One way to do this is start with a 0. And so for 0, we can say 0 is just 0 plus 1 of the width. The second value is 0 plus, that's the starting point, and we go over one space, which gives us to the 0.5. The next value then, we want to get to 1, starting at 0, so that's 0 plus 0.5 plus 0.5, which would be 0 plus 2.5s. And then one more, so we've got 0 plus 0.5 plus 0.5 plus one more 0.5 would be 3.5s. Now we can take our summation notation. We'll let the indice I, and you could use K, N, or whatever letter you want to. We start at 0 and go up to 3. Now count that on your fingers. That's actually 4 terms, right? 0, 1, 2, and 3. And the f of 0 plus I, the delta x, is the width. And then we want to make sure that we also multiply it by the width of the rectangle. Let's put in the value for the left-hand sum, and we get 0.5I and then times the 0.5. But check, f of 0.5i. When I is 0, the first point, we get that 0. The next number after 0 is 1, which will give us the 0.5. The number after 1 is 2, and 2 times 0.5 will give us the 1. And finally, when we stop at 3, 3 times 0.5 will give us the 1.5 that we are evaluating in the function. That's for the left hand. Now, for the right hand side, notice that we just shifted one of the width over to the right. And so how do we do the grid points here? Well, this time, instead of starting at 0, we're going to start at 0.5. The next place that we want to move to is 1. Then after that is 1.5, and the next one is 2. Similar to what we did with the left-hand side, we're adding multiples of the width of 0.5. And so if we put this in the summation notation, instead of starting at 0, we're going to start at 1. And again, 1, 2, 3, 4, that gives us 4 rectangles. We have f of 0 plus the indice I delta x to give us the function value. Delta x is equal to, and we put in that f of 0.5i, because the 0 doesn't change anything, times 0.5. Take a moment to look over L4 and R4 and make sure you can see what was done in shifting the index. Riemann sum definition. The sum we found to approximate the area between y equals f of x and the x-axis is called a Riemann sum. When using equal subintervals as we did in the previous examples, the width of each of the n subintervals on AB is delta x, which we write as b minus a over n. That's just the width of the rectangle. So A is our leftmost value and B is our rightmost value with n total rectangles, and A equals the first x naught value, which is less than x sub 1, which is less than x sub 2, all the way to less than x sub n minus 1, less than x sub n, and x sub n is equal to the rightmost value. And let's note where x sub 1 is equal to the initial value plus delta x. X sub 2 is equal to the initial value plus 2 times delta x, dot, dot, dot. For the left-hand sums, the heights of the rectangles are, and they start at x sub naught. So f of x sub naught, comma f of x sub 1, comma f of x sub 2, dot, dot, dot to f of x sub n minus 1. And in summation notation, we would write L sub n is equal to, and notice that for the indices of summation, we start at 0 and go to 1 less than the total number of rectangles. That is the summation of I equals 0 to n minus 1 of the function f evaluated at x sub I times delta x, which is the width. And for the right-hand sums, the heights of the rectangles are, we shift over one grid point, so f of x sub 1, comma f of x sub 2, comma f of x sub 3, dot, 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 all the way to f of x sub n. And in summation notation, r sub n is equal to, we start at the I equals 1 and go all the way to n. That shows the shift to the right one grid point. And then we have the area of the rectangle, which is the height, f of x sub y, times the width of the rectangle, which would be delta x. Error bound. Our goal is to find the actual area, which means we want to improve our approximations. The next steps towards achieving this goal is to examine the worst case scenario of our approximations, which we call the error bound. We observed in our earlier examples with the function f of x equals x squared plus 1 that f is increasing on the interval from 0 to 2 so that the L sub n is an underestimate. That is, if you use the left endpoint, you got some gaps not touching are going up to the actual curve, and R sub n is an overestimate. That is, you got some rectangles above the shape of the curve. And so if you'll recall, L sub 4 was 3.75, R sub 4 was 5.75, and the true actual area is somewhere between those two values. Let's observe that those gaps together, if we add them up, gives us an entire rectangle of possible error. So let's look at our rectangle and note that the area of the extra rectangle is f of 2 minus f of 0 times delta x. The f of 2 minus f of 0 gives you the height of that rectangle, and the delta x gives us the width. So when we compute this, okay, the x squared plus 1 is the function evaluated at 2, minus the 0 squared plus 1 is the function evaluated at 0. That gives us the height, and we multiply it to 0.5 to give us the possible error. And that ends up being 5 minus 1, which is 4 times 0.5, or 2. So we have an error bound of 2 squared units. Generally, this would be f of b minus f of a times delta x. That is the height of the total possible error times the width of the rectangle. Let's get to a theorem. If f of x is positive, is continuous, and is either increasing or decreasing, that's one or the other, on a closed interval from a to b, then the absolute value of f of b minus f of a times the quantity b minus a in the numerator divided by n is an error bound for the approximation of the area between the graph of f and the x-axis from x equals a to x equals b for either L sub n or R sub n. Example, find an error bound for R sub 8 of f of x equals x squared plus 1 on the interval from 0 to 2. What this is asking is that if you fit 8 rectangles between 0 and 2 under the curve and above the x-axis, what's the greatest error you can have? Well, solution. The previous theorem applies here because f of x equals x squared plus 1 is increasing on our interval from 0 to 2 and is also positive. So the error-bound formula works here. That is the absolute value of f of b minus f of a times the quantity b minus a, all divided by n. Let's evaluate. So we've got f of 2 minus f of 0. Okay. Notice those are the endpoints of our interval. Then we're going to have 2 minus 0. We divide by 8 because it says R sub 8, so that means we've got 8 rectangles. That's our n. F of 2 is x squared plus 1, that's 5. F of 0 is 0 squared plus 1, that's 1. So let's replace the notation of f of 2 and f of 0 with the numbers. So we'll have 5 minus 1, and the 2 minus 0 over 8 we can write as 1/4. Let's continue. 5 minus 1 is 4, and 4 times 1/4 gives us 1. That tells us that the maximum possible error we can have on 8 rectangles, R sub 8, is going to be 1 squared unit. Thus, we see that R sub 8 is within 1 square unit of the actual area between the function and the x-axis from x equals 0 to x equals 2. Note, when we computed the area with 8 rectangles was 5.1875, and for L sub 8 it was 4.1875. What's the difference between those? The 1, the error bound we just computed. Example, a researcher is investigating the value of the area between the curve g of x equals e to the power of x squared and the x-axis from x equals 1 to x equals 2. how many subintervals are necessary to approximate within 0.1 of the actual area using left subintervals. That is, find the minimum n necessary to give an error bound of 0.1. Solution. Remember, we're working with g of x equals e to the power of x squared on the interval from 1 to 2. What we want is the smallest n possible so that the error bound, so the absolute value of g of b minus g of a times b minus a over n is equal to or less than 0.1. We will set the error bound equal to 0.1 to find n and then just round up. We're going to write the absolute value of g of b minus g of a times the quantity b minus a over n and set it equal to 0.1. Now we'll put in the numbers. So the absolute value of g of 2 minus g of 1, and then we're going to multiply that to 2 minus 1 over n and set that equal to 0.1. Let's use your calculator to compute g of 2. That would be e to the power of 2 squared, and that's approximately 54.5981. Let's do the same thing for g of 1. The g of 1 would be e to the power of 1 squared, approximated to 4 decimal places, and that would be 2.7183. Now let's move on over and do the computation. Replace the g of 2 with 54.5981 minus and replace the g of 1 with 2.7183. It's still times 1 over n, and it is still set equal to 0.1. Do the subtraction, and we'll get 51.8798 times 1 over n equals 0.1. We're solving for n, so let's cross multiply the n and the 0.1, which will give us 51.8798 divided by 0.1 equals n, and we'll get that n is approximately 518.798. Again, n is approximately 518.798. What do we do with this? Well, the minimum n necessary to ensure an error bound of 0.1 is 519. We round it up. If we increase the number of rectangles from n equals 519 to n equals 5,190, then we can decrease that error bound to 0.01. The previous exercise demonstrates that the approximations get increasingly better as the number of subintervals, which are rectangles, are increased, or alternatively when the width of each subinterval is decreased. Same effect. As we do this, the left and right sums approach each other. Now let's revisit the area under the graph of f of x equals x squared plus 1 above the x-axis and between x equals 0 and x equals 2 while increasing the number of rectangles. Here, when we had 4 left rectangles, there were some clearly visible gaps between where the rectangles and the graph was. When we increase the number of rectangles to 8, notice that the gaps get smaller, and just for fun, if we increased it to 16 left rectangles, there's barely any gaps at all. Now let's look at 4 right rectangles. We've got overages that are clearly obvious. When we increase the number of rectangles to 8 right rectangles, the overages get less. And finally, when we go to 16 right rectangles, the overages get even less. The idea here is that as you continue to increase the number of left rectangles and the right rectangles, they will eventually approach just the shape. Concluding theorems. If f of x is greater than 0 and is either increasing or decreasing on a to b, then its left and right sums approach the same number as n gets real big. And theorem, if f of x is continuous on AB, the Riemann sum for f approaches a real number limit as delta x goes to 0 or as n goes to infinity. Delta x going to 0 means we are making the rectangles narrower and narrower, almost to the point where it's like 0, and n goes to infinity means that we are increasing the number of rectangles so many that it is no longer countable.